Hello and welcome to this FP2 proof video for the complex number chapter. What we're going to do in this video is prove that this part of de Moivre's theorem is true. We've done it already for natural numbers. We'll do it here for integers and rational numbers. For natural numbers, I did this in the third video of the chapter, and it looked like this. It was proof by induction, and we proved de Moivre's theorem in full to be true for all natural numbers or positive integers. What we're going to do in this video is not the full thing. I'm not going to worry about the modulus, because each time that's quite straightforward. You get one here, you get another one, and you put them together. That's not the difficult part. The difficult part is the trig part, so that's where we're going to focus. So when we do this for all integers, we've done it for positive integers, we need to do it for 0 and negative integers. For 0, it's pretty easy. We don't need an algebraic proof for 0, we just put 0 in for n and show that this is true. So obviously the left-hand side is equal to a 1, because anything to the power 0 is a 1, and the right-hand side is cos of 0 plus I sine of 0. I sine of 0 is 0, and cos of 0 is a 1. So the right-hand side also equals 1, so it is true for 0. So that's positive integers and 0. Now we need to look at negative integers. And to do this, I'm going to let n equal minus m, where m is a positive integer, therefore n here is forced to be a negative integer, and I'm going to work with this to show that it does indeed hold true. So we've got cos of theta plus I sine of theta to the power of minus m, and you know that that is 1 over cos of theta plus I sine of theta to the m. Now m here is a positive integer and we know it holds true, so I can convert this in the denominator using what we already have proven to this. And then we need to make it look in this form again, with a minus m in here and here. To do that, we need to manipulate this fraction, and I'm going to multiply top and bottom with cos m theta minus I sine m theta. Same on the bottom. And the reason we do this is because we know when we multiply I sine m theta times cos m theta minus I sine m theta times cos m theta, those two terms cancel out. So in the denominator, we end up with cos squared m theta minus I squared, so that changes to a plus sine squared m theta. And you know cos squared plus sine squared with the same argument is just equal to 1. So the denominator is going to become a 1. In the numerator, we just have cos m theta minus I sine m theta. So that all simplifies to this, which is not quite what we want, but we do also know another trig thing, and that is that cos m theta is the same as cosine of minus m theta. So I can just change that into that, and minus sine of something can change to plus sine of the minus that thing. So while this can just change to that, in order to change it on the sign, this becomes a plus. And this now is the proof complete. So this is the proof complete for negative integers. We've already shown positive and 0, so now we have shown that this is true for all integers. The only thing left is to show that it is also true for rational numbers, and you should know that a rational number is defined as a over b, where a and b are both integers. So we're going to have cosine theta plus I sine of theta. Now n is equal to a over b, where a and b are both integers, and straight away I'm going to split that into cosine theta plus I sine of theta to the power 1 over b, and again to the power a, because you know from your indices work that this is true, and the a here is just an application of what we had on the previous screen. If this is an integer, then we know that's fine when we come to do that. The question here, the heart of the proof of this, is whether or not this can be converted into cos theta over b plus I sine theta over b. And to show that, I'm going to leave this for a moment and come back to that later. What I need to show for now is cos theta plus I sine theta. If I split this into pieces, cos theta plus I sine theta to the power 1 over b, and if that b was a 2, that would be a half, so that would be like a square root, and to make this true you'd have to have a second square root, timesing them together to make the full whole again. So if this was a square root and this was a square root, this times this would equal this with a power 1. Of course, if b was a 3, then we would need another one. And so on. So we can multiply as many of these as we need to make the 1 over powers add together to give us a whole. And there are two things to consider here that make this useful. The first is that the number of terms needed, where each term is one of these things, to make this equal to a whole is b. We need b terms. If b is 2, we need 2 terms. If b is 3, we need 3 terms, and so on. So here there are b terms. The second thing then is that the root 1 over b, whatever root that is, the bth root, if you like, of this complex number will be a complex number of some kind. So if I write that as cosine, let's say a, plus I sine of a. So this to the 1 over b, I'm going to let equal this, where I don't know what a is, but I do know that that will equal a complex number. Now, allowing for what we said in the 5th video, that we actually have multiple answers to this, I'm just going to focus in on one of those answers. And we're going to have the same answer for each one, just to keep things fairly straightforward. The multiple answer thing, we addressed that in the 5th video. So let's just call this cos a plus I sine a, and then another cos a plus I sine a, and we won't worry about adding on the plus 2k pi, but of course that would be in there. As many as we need of these to make b lots of them. And of course, if there are b lots of them all multiplied together and they're all the same thing, then this must be this complex number, whatever this complex number is, to the power of b. And again, b in this case is just an integer. So we can apply this knowing that it is true for integers. But it still has to equal cos theta plus I sine theta. And because the real part here and the imaginary part both have to be equal, we can confidently say that theta is equal to ba, which tells us that a is equal to theta over b. And if a is equal to theta over b, then here cos theta plus I sine theta to the 1 over b equals cos a plus I sine a is telling us that this will come down as a multiplier inside with theta. So I'm using this fact here together with this connection that I said that this is going to equal this, and we didn't know what a was, but now we know what a is. A is theta over b. So if this thing is the same as this, then this must hold true with the 1 over b coming inside with the theta. Which brings me back to the purple line here. I can indeed replace this with a theta over b to give cos theta over b plus I sine theta over b all to the power a, and using what we already know about integers, we can now put the a inside as well as a multiplier, so that's a theta over b plus I sine a theta over b, which completes our proof that this can be written as this. So it is true even for rational numbers, and as far as I'm aware is true for all real numbers and even for complex numbers. But we don't need to prove that in this course, that's way beyond the course. The most complicated thing you'll need to use it for in this course is a rational number. I hope that helps you to be very confident when you're using de Moivre's theorem for all things in this course.